Okay, thank you, everybody. Welcome everybody to this section on Cryptanalysis II. My name is not Dmitry, but I'm still sharing. And the first talk is on improved resultant attacks against urbanization-oriented primitive. And Mael is going to give the talk. It is yours.
Thank you very much for the introduction. So let's dive right in. So a bit more about arithmetization-oriented primitives. So this work focuses on arithmetization-oriented hash functions. So first of all, to understand why these primitives work the way they work and why we have these algebraic attacks, we have first to notice that they come from the need of arithmetization-oriented. For example, if you take zero-knowledge proof, it turns out that if you try to use typical Keccak and AES, you have pretty bad performance. So new primitives were designed to have better performance for this advanced protocol. So in particular, these new protocols and hash functions operate over large finite fields rather than on bit sequence. And the goal here is to optimize the number of field multiplication rather than the gates. So there's less than 10 years of cryptanalysis, and you can find here a list, non-exhaustive lists of some of these hash functions. So in this paper, we mainly focus on 4 hash functions, which are anemoid, Griffin, Arion hash, and rescue prime. For anemoid, Griffin, and Arion, we provide improved full-round attacks. Those were already broken. And for rescue prime, we provide the first ever full-round break of an instance. So all of these hash functions, they are based on the sponge construction, and here we only target the underlying permutation. Do note that there are many different instances of each of these hash functions. They are much more like permutation family, but they all have in common one particular fact, which is that they're all based on S-box of the form either x give x to the alpha or x gives x to the 1 over alpha, which is the main thing that we will actually use. So the problem we are trying to solve here is called the SICO problem. In particular, we only target SICO1 in this case. So given a permutation pi, the SICO1 problem is as follows. We're trying to find, as the name would suggest, constraint input and outputs, so x0 up to xt minus 2 and y0 up to 1xt minus 2. And usually we do this constraint as a 0 input and output. So why do we actually care about this problem? It turns out that if you use permutation in a sponge with capacity 1, then you can pretty trivially construct some collisions. Even though that might not seem actually very useful in typical scenario, it turns out that in the arithmetic-oriented world, some hash functions just have 2 wires. So in this case, you do have a capacity of 1, and this is actually pretty usable. So the best attacks against these primitives are usually algebraic attacks for the ones with the alpha inversion, so S-box for the form x gives up to the 1 over alpha. And 2 notable attacks are the free lunch attack, which was presented here last year, and the first ever resultant attack. So to better understand what we're going to do, let's take a look at an example, which is the anemoid pi round function. So the anemoid hash function uses the anemoid pi permutation, which is itself several layers of this particular round function. So at first we have an affine layer, which is just multiplication by an MDS matrix and constant addition, which changes at each turn. And then we have this nonlinear layer, which consists of these 3 functions. But the only one that really interests us is the x gives x to the 1 over alpha, which is the only high algebraic degree 1. Because we want to do an algebraic attacks, or in other words, try to model the cipher as a polynomial, this is the only one that bothers us. And so what we do actually do to try and mitigate that is to introduce a new variable, as one does. So if we have P the inputs and the output is just Z, then we can use this property, which is also used in the proof itself, that by adding an extra variable per round, we can have this equation, which will be like Z to the alpha equals P, which is now of low degree. Consider that alpha is small. So in detail, if we add this construction, let's make this simple arithmetic and look at it. So we have input polynomial P1 and Q1, and then we can just follow up with the algebra. So now, what happens if we try to do this on multiple rounds? Well, each round we have to add an extra variable, right? And we get also an additional equation of the form z to the alpha minus some polynomial of the previous variables. So in the case of a CCO, which is what we're trying to build, what we need to do is, of course, constrain the input to this 0 and for output, and then we have to have our degree of freedom, which will be this variable x, and then we'll try to represent this output, which is the corresponding for the CCO, and try to find the root of this polynomial, or because we have multiple equations, solve the system. This system is highly structured. So first of all, it's well defined, as we have as much unknowns as we have equations, but it has this very nice property, which is that it's quasi-triangular, meaning that the ith equation only depends on x and z1 up to zi, and that the zi term is only this monomial zi to the alpha. So these are like very important properties that were already used in previous attacks, but we will try to use them even further. In particular, we can construct these polynomial CUIs such that the degree in z of the last the variable that we added, that all of the degrees of the variable are less than alpha. And I will explain this in a short moment and why we have to do this, and this is so crucial. So to better understand why we have to reduce the system as we construct it, we have to dive, unfortunately, into the complexity of the algorithm that we have to use. So first of all, quick reminder, if we have two univariate polynomials in X and we want to multiply them, this is going to be done efficiently using FFT or DDT, DT. And the usual cost that we refer to in the paper is d log g log log d, which is a big O chill of d, with d being the degrees of the polynomials. Now, because we'll have to actually multiply multivariate polynomials in our case, we have to use something that's called the Kronecker trick that I won't be able to fully explain in detail, but basically the Kronecker trick transforms multivariate polynomials into univariate ones, multiplies them, and then transform back into the multivariate form. What bothers us here is the complexity of it. It turns out the complexity is related to the product of the sums of the partial degrees, and we clearly see that if we chain multiple of this polynomial multiplication, which we will do because we have multiple rounds, the costs will become even more than exponential in n because these sums of partial degrees will also increase. So what we would like to do, and is quite intuitive, is try to bound these multivariate degrees. So all these extra variables that we have, we want them not to increase too much in degree. So let's see how we can do this. Yep. So the goal is, if some of you are familiar with, for example, Barrett reduction, is to reduce gradually. So each time we do a multivariate multiplication, we will just reduce just after this. So if we take the situation in which we are in the middle of computing this system, we already have previous variables that we added and previous equation, which we will suppose are reduced. And now we want to compute a product. So because it's already reduced, the partial degrees in these EIs are less than alpha. And then if we compute the product simply in FP, so the terminology is that we want to compute in modulo the idea, right? But first we compute in the general ring, and then we consider the product, the partial degree of the product will not exceed this 2 alpha minus 2 because they were already reduced. And so by doing this gradual reduction, we are sure that each time we do a multivariate polynomial multiplication, then the partial degrees won't exceed something so big that we have to do many steps to reduce, basically. And what this allows us to do is have this bound where we can bound all these partial degrees. And so the complexity of the whole multiplication is no less than the complexity in X, because the degree in X will, of course, increase. But with this only 2 alpha minus 1 to the n, and if we did not reduce, we would have the product of the sums of the partial degrees each time. So that's the main goal of the reduction. So that's why we can actually construct the whole system in big O chill of di times 2 alpha minus 1. Di being the degree of the ideal. So now onto the actual resultant parts. So we have constructed this system that we want to solve. And we can show that we can do this almost big O child of di with this surplus term of 2 alpha minus 1. But now we have to actually solve this system. And let's get into it. So what are resultants? Resultants are actually a very old technique of resolution for multivariate systems, where you simply have two polynomial P and Q, and you put the coefficients in a matrix in a particular way, which is called Sylvester matrix, and then compute the determinant of this matrix. The important thing here is that the polynomial base ring only needs to be a ring, and that's very important for our purposes. So let's take a look at the basic properties of resultants. If K is this time a field, then we have this nice property which is relating GCDs and resultants, which is that if two polynomials have a trivial resultant, then their GCDs is non-trivial. So that's only if K is a field, which means that they might have a common root if this GCD happens to be a polynomial form X minus R. But in general, with this more general, if the base ring is not a field, that if the resultant is null, that they have a non-trivial common factor. And that's what we'll use extensively to solve systems. So let's take a look at a simpler example, which is the main use today with resultants, which is this bivariate system. So the reason why this field ring is important is because we can really see a bivariate ring as a univariate ring in another univariate ring recursively. So what we can do if you have two bivariate polynomials is compute their resultants, find a root. So the resultant of these bivariate polynomials will be univariate, compute the roots, and then we can, if this property holds, have another roots for each of those, and we can solve the system. So this is the main use. So now this is for bivariate only. Let's take a look at why resultants are not used in the general case, because they've been actually not used very much. So if we have this general system with n equations and n polynomials, if I want to solve this system, what I will have to do is pick one polynomial in particular, for example, this one, the last one. And if I want to make basically disappear the last variable, which would be xn, I have to compute resultants of p1, pn, p2, pn, and so on and so forth. So I have to do n resultants to remove the xn variable, right? And so clearly, in terms of complexity, this becomes very bad very quickly, because the resultant, the degree of the resultant is the product of the both degrees. If I have to just do n of them to reduce one variable, overall I have to do n times n minus 1 over 2 at least, which makes at least dag of this first polynomial to these operations. And so that's already more costlier than Grobner basis techniques for n bigger than 3. So that's why usually resultants are not a great tool. But in our case, remember one of the properties I mentioned, which is that our system is quasi-triangular. So this was already presented in AsiaCrypt, this technique. Which means that when we compute this last resultant to basically remove the t variable, zt, this variable is only present in the final polynomial and one of the z, the t to the alpha minus something equation. So we only need one resultant to reduce one of the variables to basically delete from the system. And so what this makes is also that the ideal doesn't have any parasitic solution. So it's very important that we do not outgrow the system, basically. So in our case, we'll be computing several of these resultants. So of the form res, so of a polynomial p and some of our equation of the form zt to the alpha minus ut. So this is the second property I mentioned, which is that we only have this zt to the alpha monomial. And so we have a very structured Sylvester matrix. If we go back to that definition I gave of the Sylvester matrix, it looks something like this. And computing this resultant in a naive way, even though there are better algorithms for computing determinants, would cost, because this matrix is of size d plus alpha times d plus alpha, around d plus alpha cubed, right? But if we realize that this matrix has actually some pretty big sparsity, we can actually do combinations of rows and columns to reduce this matrix down. So this determinant computation. I don't have the time to explain the details, but I have some bonus slides if some of you are interested. And so we can reduce this whole computation down to what we call the special resultants, to an alpha times alpha matrix. So there are several cases here. And this matrix is also a Toeplitz matrix. So it's a special matrix that's already been studied. In practice, most of the instances we target, they have variance with alpha equals 3. We already reduced to a very small matrix, 3 times 3 matrix. We can almost consider this constant time, meaning it's very practical for practical tests of the attack. And if alpha is larger, we have better algorithms with overhead roughly alpha squared. And so that gives us this very efficient way of computing resultants. So in terms of experimental results, so here, those are round reduced. And with alpha equals 3, we have a very, very fast compared to the previous ones because the attack is very simple. We don't have any change of basis or complex Grobner basis methods. So the practical side is we almost hit the half round mark of we do actually hit it. So 11 rounds for Anemoy, and then we have also very fast attacks for Rescue and Griffin. And for the theoretical complexities for these 4-round instances, so I've selected here a few instances, so not all of them. If you have questions, you can ask me. And in particular for Anemoy, we can actually now break instances with value of alpha more than 3, which was not previously done. And for Rescue Prime, the instance that uses 512 bits of security can actually be computed in 475. So do note that all these attacks were implemented and they are available online if some of you are interested. So as a conclusion, as already said last year, AOH function designers should not base their criteria on Grobner basis methods at all, and instead conservatively consider the ideal degree DI as the lower bound. In terms of future work, we aim at using better algorithms for generic resultant computations and moving from SECO1 to SECO2, because in some cases, SECO1 is not really relevant. Thank you very much for your attention.
Thank you very much for the nice talk. Are there any questions? I have one. Can you go to the table with the complexities?
Yeah, not this one.
So what is the kind of, how do you measure these complexities? There has to be some unit and...
Yeah, so these complexities are measured in like number of bits of like basically a bit of brute force units, so in equivalent. And the way they're computed is mostly taken because of the algorithm. So we almost like take off the constant in front of this algorithm, and then this gives this like bounds of costs because of the algebraic algorithm and multiplication behind this. And it's also a big question of representation, so size. Because we have this almost optimal results for like big O tilde of di times this 2 alpha minus 1, because the system itself to represent already takes big O of di, there's only this term of 2 alpha minus 1 to the n, a term that we have to account for. So if there was any like imprecision for these results, it would only come from this term because the rest is only space.
Okay. Thank you very much. More questions? No? Then let's sing mail again. And I guess the rest is video, no? So, so the next talk is triangulating mid in the middle attack.
Our present,
and
our work,
it's online and boxing.
meet in the middle
We give
attack. I'm the author Bo Xin Zhao,
recorded the
and
video.
the other authors are Qingliang Hou. I will present our work titled Triangulating Meet in the Middle Attack. I'm the author Bo Xin Zhao, and the other authors are Qingliang Hou, Ling Yueqin, and Xiaoyang Dong. Our research focuses on efficiently solving nonlinear constrained natural words in meet in the middle attacks. The presentation will be structured around 4 core parts. I will present our work titled Triangulating Meet-in-the-Middle Attack. I'm the author Boxin Zhao, and the other authors are Qingliang Hou, Lingyue Qin, and Xiaoyang Dong. Our research focuses on efficiently solving nonlinear constrained natural words in meet-in-the-middle attacks. The presentation will be structured around 4 core parts. First, we will introduce the fundamental principles of meet-in-the-middle attack. The meet-in-the-middle attack was first introduced by Diffie and Hellman in 2077 to attack double dash. Take double dash as an example. If the plain text is encrypted to ciphertext by K1 and K2, K1 and K2 are dependent, called natural sets. The time of exhaustive search for K1 and K2 is 2 to K1 plus K2, but in the middle attack, by matching the forward computation for plain text P under K1 and backward computation for ciphertext C and K2, the time complexity is optimized to 2 to K1 plus K2 minus n, where n is the number of matching bits. Currently, enhanced techniques for this attack have been developed, such as splice and cut, initial structure, and automated tools. It has been widely applied to the analysis of hash functions like MD4, MD5, and SHA-1, and so on. In 2008, Oki and Sasaki proposed the splice and cut technique at SAC conference, which is a classic framework for meet-in-the-middle attacks, and then initial structure. Its core process includes 3 key steps. First, split the algorithm into forward and backward chunks. Second, use an initial structure to fix some variables and reduce uncertainty. Third, perform partial matching between the intermediate results of the 2 chunks to filter valid candidates. Specifically, DR and DB present the degree of freedoms of natural world. We first compute 2 to DR values backward to matching points and store them in hash table L1. Then compute 2 to DB values forward to matching point and store them in L2. And finally, find n-bit partial matching between L1 and L2 to complete the attack. The time complexity will be about 2 to h minus mean dr, db, and m. Here shows an example of meet-in-the-middle pre-image attack on a 7-round AES-like hash function. The starting states have 4 forward natural words and 12 backward natural words, while the initial structure has 3 forward constraints and 8 backward constraints. Therefore, the degree of freedom of forward and backward natural words will be 1 and 4. The matching step occurs through mixed column operation, and there are 4 matching bytes. The total time complexity is about 2 to 120. The second part is triangulating meet-in-the-middle attack. At Crypto 2021, Dong gave a formal description of the meet-in-the-middle attack involving nonlinear constrained natural words, as shown in the equations on the slide. Pi plus and pi minus represent specific constraints on the natural word of the forward and backward commutations, respectively. These constraints arise from nonlinear operations in cryptographic algorithms, such as S-box. Unlike linear constraints, which can be solved via Gaussian elimination. Nonlinear constraints involve complex mappings that make direct solving difficult. Don't propose a table-based technique to solve nonlinear constrained natural words as shown in algorithm 1. The core idea is to pre-compute all possible values of natural words and store them in hash table V and U. However, this technique has a critical flaw. It requires a huge amount of memory to store the two hash tables. If the nonlinear constraints of a certain meet-in-the-middle path are simple, the triangulation algorithm can be used to solve them instead of having to traverse and store all of them. Let's consider the following equations and Khovratovich triangulation algorithm. The core idea is to find the variable involved in only one equation and mark the variable and equation as processed, and repeat the process to remaining equations. Here, if we traverse the value of x and s called free variables, then v, u, t, z, y can be deduced and we call them dependent variables. However, if there is another equation, as in the box, only one dependent variable can be extracted and the original triangulation algorithm will terminate. That is, the original TA can only solve systems where there exists a variable appears in exactly one unprocessed equation. If no such variable exists, the algorithm terminates prematurely. To address the memory issue of a table-based technique and the problem that the original algorithm terminates prematurely, we propose an improved triangulation algorithm inspired by structured Gaussian elimination proposed in the 1990s, compiled with original triangulation algorithm. The main difference of our improved TA is the strategy for finding the variable involved in only one unproposed equation. First, we also search for a variable that appears in only one unprocessed equation. If such a variable exists, mark the equation and the variable as processed. But if no such variable is found, count the number of variables in each unprocessed equation. Then remove the equation with the most variables and mark it as processed. This modification allows the algorithm to continue reducing the number of free variables, even for complex nonlinear systems. Now let's continue to consider the equation system. The whole process is illustrated in the following matrices. After extracting y, instead of immediately mark the remaining variables as free, we analyze the number of variables included in each remaining unprocessed equation and prioritize the equations with the largest number of variables. The fourth and sixth row in the first matrix, which are highlighted in bold, label one of them as processed and remove it from the equation system. That is, move this equation to the top of the second matrix and highlight it in color cyan. Continue to process the remaining four unprocessed equations to extract dependent variables z, t, u, v sequentially, and get two free variables x and s. Once the nonlinear constrained natural words of a specific path are instantiated when given global const, we can use the new TA to solve them. The method in Crypto 2021 travels 7 bytes variables to compute B1 to B6 and store them in a hash table U. Time and memory are 2 to 56. On the other hand, use new TA and given 5B, we traverse x and i's, and deduce v, u, t, z, y, and b4, where needs a memory of 2 to 16. Based on our new TA, we summarize the method to solve the nonlinear constrained natural words in algorithm 3. First, for each combination of constant values, travels the free variables x and i's. Second, deduce the dependent variable and compute the constraint value b4. Third, store the mapping between b4 and the natural word set in hash table U, and similarly prepare table V. Finally, by matching the intermediate results of U and V at the matching point, we can efficiently filter validate natural words. Based on the new TA, we design an automatic search framework consisting of 2 steps. First, use existing MILP models to search for potential meet-in-the-middle paths for cryptographic primitives like AES. Second, apply the improved TA to each meet-in-the-middle path to solve its nonlinear constrained natural word system, and recognize the good meet-in-the-middle path with improved memory complexity. We applied the new method to AES and Ringdale. AES is a 128-bit block cipher with 128, 192, 256-bit keys, while Ringdale supports block lengths of 128, 192, 256 bits. Each round function consists of 4 operations: add round key, sub bytes, shift rows, and mix columns, which is illustrated in the following figure. For more clear, I details our single plaintext recovery attack on 5-round AES 128 as an example. The starting state RK0 contains 4 bytes of forward natural word and 12 bytes of backward natural words. The whole computation from starting state to matching point consumes 9 degrees of freedoms of backward natural word and 3 degrees of freedoms of forward natural words, and there is 1 matching byte in round 2. Denote the starting state RK0 as K0 to K50. We get the expressions for 9 consumed degree of freedom of backward natural word on A and round key as follows. Excluding the part related to blue bytes, we get the following equations, which are only related to the right bytes, where the boxed part are deleted. We express the equations in the matrix form used by TA. We first encounter a matrix where no variable appears in only one unprocessed equation in matrix A. We then remove the 3 border rows corresponding to SR31, SR34, RK50, and mark them as processed, resulting in matrix B. Here, K7 only appears in A24 in remaining equations. Extract a dependent variables K7 and label the row as processed, get matrix C. Then remove 1 border rows corresponding A114 and label it as processed, get matrix D. Process the last 4 rows of matrix D and extract K1, K2, K5, K9 sequentially to get matrix F. Finally, we extract 5 dependent variables marked in green, and the others are 7 free variables. Given the values of 7 free variables and assign the last 5 equations to some constant E1 to E5, the dependent variables are deduced in sequence. On the other hand, we can get the expressions of 3 consumed degree of freedoms of forward natural words on round key. Assign the following formulas as constant E6 to E8. we can get 3 dependent variables and 1 free variable. The 5-round meet-in-the-middle attack is given in the following algorithm. Given the global constant, we pre-compute the value of natural words and store them in a table, and then deploy the meet-in-the-middle process. The time complexity is about 2 to 120, and the memory complexity is about 2 to 40. Conclusion: in the application on AES, we significantly reduce the memory complexities of both the 4-round and 5-round attacks on AES 128 by a factor of 2 to 56. Due to the practical memory, the new 4-round attacks has been practically verified by a 4-byte partial key recovery experiment. We also propose the attacks on 6-round AES 192 and 7-round AES 256 with 2 plain-text cipher-text pairs. FIST is a second-round candidate of NIST PQC, additional digital signature schemes. The high-performance versions of FIST are based on Ring-EM. By applying the triangulating meet-in-the-middle attack, we found the pre-image attacks and then converted them back to key recovery attacks with 1 plain-text cipher-text pair on 7, 8, 9-round Ring-EM 128, 192, 256 respectively. Thank you for your attention. Please feel free to contact us via email if you have any question.
Thank you for the talk. Any questions? Good. This time it's good that there's no question because we cannot ask. And then we come to the last talk of this session, which is again online and
Hello.
Unlocking a mixed basis potential geometric approach for combined attacks, and the video is recorded by Kai Hu.
Hello everyone, my name is Hu Kan. I will present our work Unlocking Mixed Basis Potential Geometric Approach for Combined Attacks. This is a joint work with Zhang Chi, Chang Chengcheng, Zhang Jiashu, Wang Meiqin, and Thomas Peihong. We all know that in symmetric key cryptanalysis, there are many different kinds of attacks, including differential linear integral attacks, and as well as some combined attacks like differential linear attacks. A symmetric key cipher is secure when we know that it can resist all known attacks. However, this process is very tedious because we need to know that it can resist all known attacks, so we need to test all of them. However, even we have done this, it's actually still not enough because there are potentially new attacks. So a possible explanation for this is currently the cryptanalysis is highly empirical. So rather than we have some systematical methods. That is to say, if we can have a unified method to describe or predict many known and unknown attacks, then it will be very beneficial to us. In recent years, Ben have found the geometric approach has such a potential to unify the viewpoint of cryptanalysis So this idea is to use the linear algebra to study the attacks. Firstly, we can regard all elements in F2n as 2n basis vectors, and after choosing a field K, then we can construct a linear basis in this space, linear space. In this space, the element is the linear combination of all basis vectors derived from F2n in this way. And regard the input and output of cipher E as the key-free vector space, then we can define a linear extension of a nonlinear cipher E as TE in this way. So every input basis is mapped to the output basis vectors. You can verify in this way TE is indeed a linear map because it is closed to addition and scalar multiplication. Before I introduce the main work, I need to introduce some notations frequently used in this work. So Fu will be a function from F2n to the field K. And a vector Fu can be written in this way where X is the index. And for a basis, which is a set of basis vectors, we can write it into a matrix. And every column of this matrix is a vector, is a basis vector. And the element in the intersection of X row and U's column is just the value of Fux. Here I will introduce 4 frequently used functions in this work. The first one is called delta U function. Then only when the X is equal to U, then it's 1, otherwise it will be 0. And the second function is written like this. Only when U, the inner product of U and X is 0, then it's 1, otherwise it will be -1. And the XU is a monomial function. Then when X is partially larger or equal U, then it is 1, otherwise it will be 0. This is similar when U is partially larger than X or equal X, then it is 1, otherwise it will be 0. So with Ben's ideas, TE is a linear map. So if we find a basis for the input space and output space, here the space will be the key-free vector space. So we will get a matrix of T of the linear map TE. So if we regard the delta U as the standard basis for the input and output space, then the corresponding transition matrix will have elements which can be written in this way. So if E is a bijective function, then TE will be a permutation matrix that every column, every row and every column will have only one element 1. Next, we will consider if we use another matrix for the input space and output space. What is the corresponding matrix looks like? From the linear algebra, it's actually obvious that A will be a similar matrix of T. And the expression of A can be written with this way. And with the knowledge of the change of basis matrix, we can write it like this. So our idea is very similar to previous method. We just found that it is not necessary to use the same basis for the input and output. We can indeed use different bases for the input and output. And the calculation is very similar to previous one. So A can be calculated from the change of basis matrix and the knowledge of T in this way. Just change the F in previous works with G. It is important to stress that the possibility of using different basis in geometric approach had been mentioned in Ben's thesis, but he and others have not really explored it in cryptanalysis. So this is the first work to study it in practice. With the expression of A, then we can calculate the expression for every coordinate of this matrix. So finally, the formula is like this. Now the problem is to find some bases. We have already know 3 kinds of bases, called the standard basis, linear basis, and arithmetic integral basis, which are all from Ben and his collaborators' papers. Because every matrix that is 4 rank can be used as a matrix, so any operation that can preserve the rank can be used as a rule to generate new bases from known ones. Here, I will introduce 3 simplest rules called inverse transpose scale. If a matrix is 4 rank, then after these 3 operations, it's still 4 rank, so it still can be used as a matrix, as a basis. With these 3 rules, we can generate 4 new bases from the existing ones. Finally, we concluded 7 kinds of bases. So choose one for the input, choose one for the output, and then we replace the effect of input and output with the elements in this formula, then we can get the expression for different attacks. According to if we use different or same bases for the input and output, we can divide the cipher into 2 kinds. The first one is called same basis, and the second one is called mixed basis. In previous Ben's papers, same basis attacks have been studied extensively. So our work is the mixed basis attack. To study the mixed basis attack, we can use a similar way. Firstly, we divide a cipher E into 3 parts. And then we can study E0 with a same basis attack, and E2 with another same basis attack. And E1 will be the switch. We apply a mixed basis attack on E1. In this way, we can make the mixed basis attack easily to apply, because E1 we can always choose E1 as a very simple layer of S boxes. Then for the S boxes, it's easy to construct the transition matrix with different bases. So here it's actually very similar to the boomerang connectivity table, where we will divide the cipher into 3 parts, and in the middle part we will do the switch. Let's see some examples. So the linear cryptanalysis is a typical same basis attack, because the input basis and output basis are the same. And the recent arithmetic integral cryptanalysis is also a same basis attack. Now I will introduce a new one called subspace propagation. This attack is not a new one, because the subspace propagation or subspace attack has been studied in previous papers. But our work is that we can use the geometric approach to study these known attacks. So if we choose this as the input basis and this basis for the output, then we can get such a formula. So if you can, this expression, you will find this is exactly the number of x and ex, the platex and the suffix pairs, where the platex is inside one subspace and the ex is inside another subspace. So we can use geometric approach with a mixed basis style to describe these properties. This is not known before. until now, we have introduced the attacks with one message in a sample, such like linear cryptanalysis. But in many cases, actually, we want to use several messages. For example, typically, the differential attack, we will use 2 messages in a sample. So we need to consider the high order case. A space is if the order of a space is D, then we can find a product of D F2N space. Then we can construct a one-to-one map from this space to our target space. Then the order of this space is called D. For example, in a rectangle attack or boomerang attack, we will use 4 messages. But if we add restrictions to the 4 messages that their sum is 0, then the order will not be 4, but 3. If an attack takes plaintext subtext samples from a disorder space, then we call this attack a disorder attack. In a disorder attack, we will actually consider suffer in this way. The input will be the value, the first value, and the difference between the first value and each value after. And the output is also the output value and the output difference between the first value and the values afterwards. Then the basis for a high order space can be constructed with the basis for the single space. If Fu xi is a basis for the i's kf2n, then a basis for this high order space can be constructed with the chronic product. Also, here are some examples. The first one is the differential attack. It's a same basis second order attack. And this attack has been studied with the Quaesson differential techniques, which was proposed by Ben and Riemann in Crypto 2022. And this attack has been extended to the Quaesson D differential attack, where this order basis is used. So in our paper, we introduce a new method to studying the differential linear attack. So we choose a differential basis for the input and a linear basis for the output. Then we can construct the expression to studying the differential linear attack. In our paper, we give 4 example applications with the framework. The first one is an alternative method to studying the same property which has been studied in the arithmetic integral cryptanalysis with the mixed basis style. Then this property can be described in a much more natural way. And the second application is the multiple of n property for scanning. This property is a structural property. So from previous papers, they are analyzed with some structural property, but not the automatic search method. But in our way, we can do the automatic search, so it's easier to do it. And the longest distinguisher of a multiple of n property for scanning 64 is only 5 rounds, but in our paper we can reach 11 rounds. Finally, we verified 2 differential linear distinguishers of Simon ciphers without the round independence assumption. Let's do the summary. We explored the possibility to use different bases in Ben's geometric approach. The geometric approach becomes more flexible if we use the mixed basis style. And it can be applied to more attacks now, especially for some combined attacks. Actually, after this paper, we also developed a paper that handled the boomerang attacks with a mixed basis attack. So all attacks can be studied in a unified automatic search method. And we have applied mixed basis approach mix-based geometric approach to several known attacks and provided a new method to studying them. Thank you very much for your attention.
Thank you very much, Kai. If there are questions, please reach out by email. And that concludes the session. So let's thank all speakers of the session again.